So we've covered ionic compounds. Now we're going to turn to another group of compounds, the molecular compounds. These are ones that are covalently bonded atoms, and these are going to be nonmetals. We can't figure out the formulas just real easily like we did with the ionic compounds because there are no charges involved. And between the same two elements, there might be a whole bunch of different compounds. An example given here is compounds between nitrogen and oxygen. There are actually 6 unique molecular compounds between nitrogen and oxygen. So we can't just call this nitrogen oxide, because which one are we talking about? And there are no charges involved to help us know how many of each ion there are. And so here we're going to use prefixes to specify the numbers. So, very important, molecular compounds are composed of 2 nonmetals. These are the same prefixes we saw for the hydrates, and the problem with them is that students like them and they want to use them everywhere. We don't need to use them for the ionic compounds, and so we don't. We need them here. So avoid the temptation to put a whole bunch of prefixes into your ionic compounds. So we use the prefix to say how many atoms of each element are present. We've got 2 nonmetals. One has to go first, and the other has to go second. You don't actually end up needing to predict which happens because I'll either give you the name or I'll give you the formula, and you just keep the order the same. But some of you might wonder, well, why is nitrogen first and oxygen second? That's because we put the more metal-like element first. It's like we know they're both nonmetals, but which one is closer to the metals, right? You look on the periodic table, you've got nitrogen and oxygen. Nitrogen is on the metal side of oxygen. If you keep going to the left, you'll run into a metal. And so we put nitrogen first. Okay, so those are the prefixes. And here's the general form. So the prefix comes before the element name. And like the cations, the name of the first element is just its element name. You don't change anything. There's a prefix in front to tell us how many. There's a little space, and then a prefix to tell us how many of the second element. The second element is acting like an anion, and so changes the ending of her name. Now, sometimes we omit a prefix if it's the prefix mono, meaning 1, especially if it's on the first element. Just like we've been not writing ones in our formulas, we sometimes leave the mono out. So an example here, NO2. If we strictly follow this pattern, the name of the first element is nitrogen, and the prefix for 1 nitrogen would be mono. And then oxygen, there's 2 of them, so the prefix is di, and you change oxygen into oxide. So you might expect this would be mononitrogen dioxide, but we frequently drop the mono on the first element. And then we've got these 2 guys, H2O and NH3. I think you're already familiar with H2O, that's water. Can you give it a systematic name according to this pattern? Sure you can. It would be dihydrogen monoxide, right? So you can use that to mess with people. My teacher made us drink dihydrogen monoxide today. I think I'm going to die. It's water, right? It just sounds scary when you use a chemical name. And this is another one that's very common, NH3, always called ammonia. Its name should be nitrogen trihydride, but nobody ever calls it that. Okay? It's always called ammonia. So you need to know the formulas for water and ammonia. And you need to know, if I give you the formulas, that this is what they're called. Okay, so 2 exceptions. So let's name some things here, right? Name the compound N2O5. So let's just practice. We're always going to check what kind of a compound is this. And you do that by looking at the first element. First element is N, nitrogen. Is that a metal? No. So I've got two nonmetals. I can use prefixes. So this is nitrogen. What prefix do I put in front of it? Di for 2. So that's di-nitrogen. And then for the oxygen, I've got 5 of them. Penta. And then oxygen is acting like the anion, so she changes the ending of her name. Dinitrogen pentoxide. I got the oxide because this is oxygen. And we changed the ending of the name. And you might wonder, well, why do you need to do that? Well, because they decided. And so then I like to make up reasons. You know, there might not be any better reason than they decided that's how we're going to do it. So then we just have to do it. What makes sense to me is if I left the element name, dinitrogen, pentaoxygen, it kind of sounds like maybe there's supposed to be some more. And so the "ide" is sort of like the period. It's like, okay, this is the end of the name. So all of the molecular compound names are going to end in "ide." So that second element will have "ide" in its name. Here we've got phosphorus tribromide. That's the end of the name. So what's the formula for phosphorus tribromide? PBr3. The prefix comes before the name. The subscript comes after the name. There's no prefix here. It's not monophosphorus. And so here, P, I don't write a 1 either because, we just have a thing against the number 1, I guess. Any questions? There are a bunch of compounds that have more than 2 nonmetals, but we're not going to learn how to name them, okay? So you might occasionally see a name that's like, wait, where did that come from? There's a lot of other stuff out there. We're just going to limit it to binary molecular compounds, 2 nonmetals. And then a third group are acids. So acids can be defined in many different ways. What we're going to go with right now, an acid is a molecular compound that releases hydrogen ions when dissolved in water. So an acid has to have hydrogen ions. It has to have hydrogen in it somewhere. It's a molecular compound. It's going to be nonmetals. So acids are composed of hydrogen, which is usually written first, and then 1 or more nonmetals written second. So we identify, in Chem 1A at least, an acid because its formula starts with the letter H. If it starts with H, it's an acid. Now, these are molecular compounds. So HCl, pure HCl is a gas at room temperature. And it has a name. We can name it according to the molecular compound names. What would we call that? Hydrogen monochloride, right? Because it's 1 hydrogen and 1 chlorine. Hydrogen monochloride. When that is dissolved in water, it forms ions. It's not an ionic compound, but when it dissolves in water, it forms ions. And it forms an H plus ion and a Cl minus ion. When we put AQ in parentheses, that means aqueous, dissolved in water. So a compound is not considered an acid if it doesn't dissolve in water. I'm not going to try to trick you with something like that. Just quick overview. Characteristics of acids. Acids taste sour. Any of you guys like Sour Patch Kids? Yeah, my kids love those things. I can't stand them. They are so sour. Ick. You know what the sour is? It's acid. Why do lemons taste sour? They've got acid in them. Is that going to kill you? Is it going to make you high? No, there's all kinds of different acids, right? So acids taste sour. We're not going to taste them in the lab. Acids will dissolve many metals, not all of them though. You can dissolve things like zinc, iron, magnesium using an acid. But you can't dissolve gold, silver, or platinum. And the formulas for acids generally start with H. And that's what we're going to hold on to. So HCl, H2SO4, we should identify those as acids because the formula starts with H. Okay? How do we name these? Well, there's two kinds of acids. There's acids that have oxygen in them and acids that don't have oxygen in them. So your book refers to the ones without oxygen as binary acids, and then these are oxyacids. I refer to them as oxyacids and the other kind. So oxyacids are going to have hydrogen and some oxyanion, like bromate or chlorate or something like that from that list that we learned. These binary acids, just two elements, hydrogen and something else. So these two different groups have different patterns for their names. So the binary acids, almost always just two nonmetals. And here we're going to use the prefix hydro. So we're going to use the prefix hydro to specify the hydrogen, and then use the base name of the nonmetal. So if it was chlorine, you take the chlor and you change the ending to ic, and you put the word acid at the end. So all of the acid names have the word acid in them. Makes it nice. So let's look at how this would work. So name the acid HFAQ. So it's telling us to name it as an acid. We also have the AQ here. Technically, if you had HF gas, you should not name that as an acid. But again, I'm not going to try to trick you on that one. If you see an H, give it the acid name. So how do we name that? Hydro, that's what's standing in for the hydrogen. And then for fluorine, fluoric acid. So that's hydrofluoric acid. And I just want to point out that fluorine is gluten-free. There's no flour in fluorine. Okay, it's UO. Fluorine. And again, I won't mark you wrong if you spell it that way, but I will laugh at you. Just saying, because I think it's funny. Hydrofluoric acid. It's kind of powdery, I think. So the other kind, oxyacids. The names for the oxyacids are derived from the names of the oxyanions. So you look at the acid and you figure out, well, what's the oxyanion in here? Those are the things I made you memorize. So we got those already. And we're just going to change the ending of the ion name. So most of those polyatomic ions, fluorite, chlorate, they end in ite or ate, right? So if it ends in ate, we're going to change the ate to ic. If it ends in ite, we're going to change the ite to us. So we're going to get the base name of the oxyanion plus ic, and then we add the word acid. So you get things like hydrochloric acid. Chloric acid, or chlorous acid. So how do you remember that ic and ate go together? Well, the one I've always used a silly sentence. Rick ate him before he could bite us. There's the ite. Use your imagination there. Rick ate him before he could bite us. Another one students like is the white mouse ate icky cheese. So there you've got your ite and your us. Ate icky cheese. So we need to associate ate and ick, ite and us. There's a lot of things in this class that we'll see where we have these two things and we have to remember how to pair them up. You get a 50-50 chance, but that's not going to do so well on an exam, right? So I find these little tricks to help me remember them. And so these sentences can help you with that. So let's look at this one. Name the acid HNO2. And again, we see this AQ after it. We see that this is starting with an H. That says, this is an acid, okay? Is there oxygen? Yes, there's oxygen. So we're going to name this based on the name of the anion. So cover up the H, and what do I have left? I've got NO2, right? NO2, we memorize that has a -1 charge. What's the name of that? Nitrite. Nitrate is NO3 minus, and this is nitrite, right? So ite and ick go together. So I'm going to change this ite ending to ick. So nitrite becomes nitric, and the word acid. I was testing you to see if you were paying attention. No, I wasn't. It's Monday morning. Ite and ick don't go together. Ate and ick go together. See? Duh. Okay. Thank you for giving me the stink eye. This is nitrous acid. Okay? So easy to make that mistake. Rick ate him before he could bite us. The white mouse ate icky cheese. Write it out if you have to. You know, when you come and take an exam, whatever you bring in your head is fair game, right? Now, what happens sometimes is students, as soon as they start reading questions, what happens to your brain? Everything leaves, right? And you're like, I can't remember my name, right? And you're just like, ah. So if you're one of those people, what you might want to do is just flip the exam over on the back page before you look at any of it, which will, just erase your brain immediately. Write some stuff down. Write some stuff down like the white mouse ate icky cheese before you forget it. And then you can go back and look at it, right? So any questions about nitrous acid? Let's write the formula for perchloric acid. So we can tell from the name that this is an oxyacid because the other kind starts with hydro, and this does not. So perchloric comes from perchlor. It goes to 8. So this comes from the perchlorate ion. So I'm going to write the formula for perchlorate. Perchlorate is one more oxygen than chlorate. So chlorate was ClO3. This is ClO4, same charge. To make this into an acid, I'm going to combine it with hydrogen. The charge on this ion tells me how many hydrogens I need. And so this is HClO4, and it's best to put AQ there. Any questions? So we kind of just did this, but how do you write the formula for an acid? Anytime you see acid in the name, duh, it's an acid. That means the formula is going to start with H. Okay. We write the formulas treating it as ions, even though it is a molecular compound, because when you put it in water, it forms ions. If we see the prefix hydro at the beginning, that means it's a binary acid. It's just going to be hydrogen and something else. If there's no prefix, then it's an oxyacid, and we look at the ending ic, we change it to ate, us changes to ite. A couple more examples. Let's write these formulas. Hydrocyanic acid. Is this a binary acid or an oxyacid? It's binary because it's got that prefix hydro, right? So that means I've got this cyanic. What does that come from? Cyanide. Very good. That's not an element, is it? But we know what cyanide is. What's the formula for cyanide? Cn minus, right? So hydrocyanic acid is composed of hydrogen ions and cyanide ions. The hydrogen ions are H+. We look at the charges and we see, well, that must be HCN, and we're going to put AQ. That's named according to a pattern for binary acids. Does that have 2 elements in it? It's got 3 elements. That's why I don't like to call them binary acids, because this guy messes it up. That's the only one we'll run into, but it bugs me. Any questions about that one? Phosphoric acid. Oxyacid or other kind? Oxy. If it doesn't start with hydro, it's an oxyacid. Most of them are oxyacids. So phosphoric, this is based on what ion? Phosphate. So I need the formula for the phosphate ion, PO4 3-. To make it into an acid, I'm combining it with hydrogen ions. Hydrogen is over there in group 1, it's +1, right? So the charge on this anion tells me how many hydrogens I need. So this is H3PO4 aqueous. Any questions? How about this guy? Hypochlorous acid. Oxyacid or other kind? It's an oxyacid. This was a little tricky because hypo and hydro, really similar, right? But this is hypo. So this comes from hypochlorite. Ite and us. Hypochlorite ion. So ClO3 is the chlorate. ClO2 is chlorite, the light version. And hypo is 1 less than that. It's only got 1 oxygen. I'm going to put hydrogen ion with that to make it into an acid. And I see I just need 1 of each. And so this is HClO, aqueous. Any questions? This is interesting, but I'm not going to test you on it. You probably have heard of acid rain. Certain pollutants, such as nitrogen monoxide, nitrogen dioxide, sulfur trioxide, that are formed, from combustion of carbon, fossil fuels and things, they will form acids when they mix with water. There's a lot of water in the atmosphere, and so you can make sulfurous acid, nitric acid, nitrous acid. And so the pollutants in the air combining with water form acid, and then the rain is acidic. and that has a lot of negative effects on the environment. You see things like this where the acid rain has damaged the trees. Here we see two very old statues, but this one has been exposed to rain, and this one was sheltered, probably because there's some sort of a roof hanging out here, and we see that this one is just like eaten away by the acid rain.